Okay, so our final speaker before lunch is Nouy from the Université de Nantes, where he's a professor of in the computer science and mathematics department. He's worked on several aspects of UQ, and in particular in low rank and sparse tensor methods, and other aspects of solving PDE models with certain parameters. And today he's going to talk about principal component analysis for learning tensor tree networks.
Thank you very much for the introduction and invitation. So my talk will be about, I would say, a follow-up of what was presented by several speakers this week about these tensor formats for approximating high-dimensional functions. I will try to give another perspective, another view to complete the previous presentation and not to repeat the same type of introduction. And at the end, the second part of this talk will be about an algorithm based on principal component analysis for estimating approximation in these formats that we have seen this week. So I will first set up the context. So here we are in the context where we want to approximate a random variable y as a function of variables, random variable x, possibly many, x1 to xd, using only samples of the pair of variables x and y. This is a traditional setting in statistical learning. The standard statistical learning setting is where you have independent samples of the pair of variables x and y. Okay, so usually independent and identically distributed samples of this. The last part of the algorithm I will show you will be in another setting called sometimes active learning setting, where you are able to select the samples of x for which you are able to evaluate the corresponding sample of y. Okay, so in other context, in a deterministic setting, you would say these are adaptive sampling algorithms in order to approximate functions. Okay, so in this setting of active learning, I will be able to sample x where I want, okay, and evaluate a function to have the corresponding sample of y. Okay, so a typical setting, of course, and the setting of interest this week is the case where y is the output of a numerical model, typically a computer code, but it could be also an experimental setup, and x are a set of input parameters of the model that describe the uncertainties. And here I will assume that I know the probability distribution of the x, okay, and what I want to do is construct an approximation of y as a function of the input, and this approximation will be used as a surrogate model, okay, as was presented by Benjamin and many other speakers this year. We want to replace the model, which sometimes is really costly to evaluate, by an approximation. Well, so but in this situation where you have a very costly numerical model, only a few samples are available, and what we want to do here, approximating a function of many variables, become a very difficult task using only a few evaluation of the function. So for this you will have to exploit low-dimensional structures of your high-dimensional functions, and here you have plenty of possibilities, and we have seen several ones this week. So in fact, in my talk I will try to give you a very brief and simple overview of different approximation formats that are typically used in high dimension for high-dimensional approximation, to go slowly to the topic of interest of my talk, which are low-rank tensor formats, and I'll try to I hope to give you some connections between all these formats that are used typically in statistics or approximation of PDEs and so on. Well, so let me start with very simple and maybe most famous model in statistics, a linear model where you are in. So I would say a first comment about all these formats in high dimension. What we want to do is approximate a function in a class of functions that are parameterized by a small number of parameters. By small, when we talk about high-dimensional approximation, is typically this approximation has to be described by a number of parameters which scales linearly or, let's say, polynomially with the dimension, okay, but not growing exponentially with the dimension. So first example, linear model, of course, the number of parameters is d, O of d. But of course, this is typically not sufficient for all the models we have seen this week. So you can go to more complicated polynomial models in high dimension, and this was presented by Catherine this morning. This has a name when you use not canonical canonical monomials like this, but orthonormal polynomials with respect to a measure. This is named polynomial chaos expansion. But the idea is to have an expansion, a model which is an expansion on a set of polynomials, but where you only retain a few polynomials in I dimension. Okay, so you can either fix a priori the set of multi-indices you will retain here in the expansion, and there are some works, there have been many works on how to choose this lambda a priori, but you can also propose adaptive method in order to find a good lambda. So this in fact enters the field of sparse approximation with a particular basis, which is here a polynomial basis. Well, so another type of model in I dimension, also very used in statistics, is additive models, so a sum of univariate variables, and you can generalize a little bit this format by saying I try to find an approximation as a sum of functions of groups of variables. So of course, if you know the groups that are pertinent, what are the interactions between the variables of your model, then you can give a priori this set of groups of variables to retain, but usually you will have to do it adaptively, and then you enter again the world of nonlinear approximation. Similar things, these are additive models. Related models are multiplicative models as a product of univariate variables, or more generally a product of functions of groups of variables. So this, maybe you have seen this kind of models that are typically used for approximating density in I dimension. So of course you recognize here an assumption about the independence of variable if your density is written like this. And this form of approximation is what is called Bayesian networks or graphical models under some assumption on the set T you have here. Well, so now I go further, and what we can find also are models that are composition of functions. Composition of a function f and a function j, where both f and j have some low dimensional structures. Okay, so a first example, and we have seen this in the talk of Olivier Zam this week, are these reach functions where you have a function of a linear function of x, okay, represented here by a matrix W, and then the idea, at least in the talk of Olivier, was to find a matrix with a small number of rows, so which is associated with a map which goes from Rd to Rm, m lower than d, and then you have a problem of approximation of a function f of a smaller number of variables. Okay, so typical example is when you, for the f, you use an additive model. If you do this, you have what is known as a projection pursuit model, which is a sum of univariate functions, but these variables are linear transformation of the initial variables. Okay, and an even more specific format, which is a particular case of this, is when for the function f you take something very simple, which is a rescaled and shifted activation, so-called activation function sigma and fixed function sigma, and you obtain what is called a shallow neural network. Okay, each function here being called sometimes a perceptron. Well, so another way of reducing the dimension, so for the choice of j, you can also use sparse function. In this one typical example is here when your function j, the different components of j, will only be dependent on a group of variables. Like here, the first component of j will be dependent on the first two variables, the second on the next two variables, and so on and so on. So you use here and here different structure for the application j, but at the end, okay, you reduce in some sense first the dimension with the application j, but then you have the task of approximating the function f. Well, and if you go further, if you use more composition of functions, you arrive in the world of what we call deep neural networks, where if you use some sparsity in the j1, j2, as I previously introduced, you obtain particular cases of famous networks called deep convolutional networks that are models like this, where you have here a function of x1, function of x2, and then a function of f1 of x1 and f2 of x2, and you repeat this hierarchically like this. Okay, so this format is associated with trees of dimension. So this format of approximation is associated with this balanced tree. If you go to different trees like this, you have other networks. So this one is called a deep recurrent network with an approximation of the same type where the variables are combined differently. So I wanted to introduce this. So you see we have started from linear model, additive models. We went to composition of function and composition, and we arrived to this type of formats. So now we'll move to what is the topic of interest of this talk, low-rank tensor formats, and I will then try to convince you that there is a connection between what I have presented here and what comes later, and it was suggested also already by Lars this week. So low-rank format. So I don't want to go here into technical details about the interpretation of multivariate functions as tensors, but let me to trust me at this step. I will come back later on the functional analysis setting. Here I will just mention this, that a multivariate function can be identified with an element of a tensor product space of vector spaces of functions of the individual variables. Okay, I will clarify this later, but see just this as a tensor just to understand the language that comes now. So a function with rank 1 is simply a function which is a product of function of univariate variables. So here you recognize the multiplicative model that I have presented before. A function with canonical rank R, was presented by Lars already this week, is a function that is a sum of R function like this. Okay, so it can be interpreted as a sparse approximation in a dictionary of functions picked in the multiplicative models. Okay, so Lars I said a lot of things about the difficulties associated with this kind of format. I would like to mention just that the additive models that I have presented before, it included in this one. So if you can see that an additive model is the sum of d terms of d univariate functions. So of course, if you take all functions but one constant, you obtain an additive model. Okay. Well, but there are many difficulties, and which has led to people to introduce other formats in low-rank formats in high dimension. So the formats I want to consider here in this talk are these based on the notion of alpha rank. So first, you have to define this notion of rank for a subset of variable alpha. So I consider alpha, which is a subset of 1D, a group of variables, in fact. And I will identify the multivariate function with a bivariate function, a function of two groups of variables. If you do this, you can define, as usual, the rank of this bivariate function, and it will be called the alpha rank of the multivariate function. It will be the minimal integer such that your multivariate function can be written as a sum of product of functions of groups of variables. Okay? So if the alpha rank of your function is 2, that means that you have a sum of two products of function of groups of variables like this. Okay? So now, of course, this is not sufficient to reduce the dimension. So maybe you have split your set of dimensions into d over 2 and d over 2 variables, but still you have high-dimensional functions here in this format of approximation. So what you will do is impose more and more structure to your function by imposing the rank for many groups of variables. Okay, so you will introduce T, a collection of subsets of your set of dimensions, and you will consider what we call a tensor format as a set of functions whose alpha rank is bounded by some integer, okay, for any alpha in this collection of subsets of variables that you have chosen. So if you do it completely arbitrary, you arrive to something which is not that you cannot represent, parameterize explicitly, but in a specific situation, which was presented by Lars, and you have seen the construction in the talk of Lars Lavidic. In the situation where T has a tree structure, then in this case, we know explicit parameterization of this of functions that lives in this set. Okay, so of course there is a question of how to choose the T, because one particular T will give you a particular model of approximation. So you have several ones here that are famous. If you take a trivial tree with one level, you arrive to the so-called Tucker format. If you choose a balanced tree, you will obtain the hierarchical format introduced by Hackbush and analyzed also by Lars Grasidik. And this associated with a linearly structured tree leads to the so-called tensor train format. Okay. So now I will not go into the detail, but if you make the two presentations, I don't want to spend too much time in the explicit representation of this because Lars did it. If you combine the two presentations, you will see that at the end you arrive to an explicit representation of a function in these formats. But here I use another point of view than the one introduced by Lars. What you can show, in fact, is that the function v of x in this format associated with such a tree will have such a representation. And here you recognize what we have seen previously in the deep networks, okay? But where something is specific here, in fact, for the function of the univariate, of the individual variables here, these are maps, in fact, from the set on which your variable is defined to RR, okay? So it's a vector valued function here. You can interpret this in statistics as a feature map. You can see it like this. You can interpret this as a set of R functions of an individual variable. But then all the other functions that are functions of multiple with multiple inputs are specific functions. They are multilinear functions. Okay? So if you have a node alpha with several children, beta 1 until beta s, the function f alpha that you see in this representation is a multilinear function on a product of Euclidean spaces to Euclidean spaces. And of course, multilinear map from this to this can be identified with a tensor. And if you identify it with a tensor, you have the classical representation of this tree-based tensor format. Okay? But here it's another look at this tensor format where you see clearly the connection with the deep networks, but with something very specific here, the nature of the function that you have here, and which will give a lot of interesting property in practice. And they are listed here. So first, the number of parameters, which is the storage complexity of this format, scales linearly with the dimension and polynomially with the rank, with a polynomial exponent here which is related to the maximal number of sons for the nodes of your tree. It's called the arity of the tree, the little s that you see here. Interesting property is that the set, as it is constructed, and it was mentioned by Lars, is an intersection set. In fact, an intersection of sets of functions with an alpha rank which is bounded. Each of these sets is a closed set. So as an intersection of a finite collection of closed set, it is a closed set. What is the nice property behind this is best approximation problems are well posed, which is not the case with the canonical format, as was mentioned previously. Also interesting geometrical properties that have been proven. It's a smooth manifold, so there are interesting consequences in optimization and dynamical approximation. And last comment, and that I will use now in the algorithm I will present, is that okay, we enter the field of nonlinear approximation with this set. It's not convex. It's a really strange nonlinear manifold, but not so nonlinear in the sense that, in fact, the approximation that you have here is linear in each of the parameters here. Okay, so it's a multilinear approximation. And this very specific structure will allow to design robust algorithms, as I will show you, to find approximations in this format. Well, so now the algorithm I will present is based on an extension of principal component analysis to this multivariate function setting. So assume that the variable x nu, so this random variable has a probability law mu nu with a certain support, which is here, and let h nu be a Hilbert space of functions defined on this. Okay, so typically think about L2 functions defined on this set, equipped with the probability measure mu nu. But you can also think about reproducing kernel Hilbert spaces in L2. Okay. So then, now I formalize a little bit what I said previously, the identification of a multivariate function with a tensor. What we call an elementary tensor product between function on the different spaces h1, h2, and so on, is no more than a multivariate function which is a product of univariate functions. Okay, and then you can define a Hilbert tensor space by taking the linear span of all functions like this, okay, and taking the completion with respect to certain topology. So here, what I will use for the result I will show is the tensor Hilbert space associated with a canonical norm, okay, which is a unique norm associated with an inner product satisfying this cross norm property. Okay, the norm of an elementary tensor product is the product of the norm of the individual function. So not so important, just to clarify that the results I will show you are with respect to this topology. Okay, but think, if you want a clear message, think about the L2 space, which is a particular case of such a space with this canonical inner product. Okay, think about L2. Well, so now before going to PCA, so I will recall you what is a singular value decomposition for functions. So here I consider a subset of variable alpha. I identify, as I did before, a multivariate function with a bivariate function u, which is an element of a tensor product space, product of the space H alpha of functions of group of variable x alpha and H alpha complementary. In this Hilbert setting, it is known that this bivariate function admits a singular value decomposition. Okay, a sum of singular values times singular functions on the left and on the right. Okay, these are functions of groups of variables. Well, what is also well known is that the best approximation of your function by a function with the alpha rank bounded by R alpha, okay, is given by truncating this decomposition after R alpha term, okay, by retaining the largest singular values. Okay, this is called a truncated singular value decomposition up to a certain rank. And these functions that you see here, that are singular vectors, left singular vectors of U, are called, in fact, principal components of U associated with a group of variable alpha. Okay, I call them alpha principal components of U. Well, so here a different view at this problem is that if you define the space U alpha as being the linear span of these principal components on the left, okay, then the best approximation is obtained by the orthogonal projection of U on the tensor product space of this alpha principal subspace and the space H alpha complementary. Okay, this is another point of view where I interpret the best approximation problem as the research of an optimal subspace. And in fact, this subspace of principal components is a solution of an optimization problem like this, a minimization problem over all subspaces of a given dimension that minimize the distance between U and its projection on this tensor product space. Okay? In the L2 setting, a probabilistic interpretation of what you see here is that you minimize over all subspaces the expectation of the square of the distance between partial samples of your function. Okay, you see here, I evaluate U for some sample of x alpha complementary. This is a function of a group of variables. I compute the distance to the projection of this function of the group of variable x alpha. So what you see here, this distance is a random variable that depends on the group of variable x alpha complementary. Okay, and I take the expectation as the square of this distance. Okay.
Expectation with respect to what?
It's an expectation to what remains random, which are the complementary variables here, x alpha complementary. Okay. So now, how to extend this notion of PCA when you have this tree-based format? So consider that you have a tree like this. So the idea will be not to estimate the alpha principal components, the true alpha principal component of a function, because usually these functions are functions of many variables, so you will not be able to obtain them exactly, but we will try to approximate them. So what we will do in practice is compute, in fact, spaces U alpha associated with the different norms that just approximate the alpha principal components of U. And in practice, it will be done by approximating these subspaces in subspaces of small dimension. But I have to tell you now what are these spaces in which we will try to approximate the principal component. So for each node of the tree, the idea will be to compute the alpha principal subspace, not of U, but of a projection of U on a low-dimensional space V alpha. If alpha is the leaf of your tree, so you will start from the leaf of your tree. Consider you have on the first leaf, leaf 1, which is associated with functions of the first variable. What you will do is here introduce an approximation space in your space H alpha. So typically polynomial approximation, wavelet approximation, could be perceptrons, or I would say it depends on the context. You can also work with adaptive methods for the choice of the space, but here I will show you an example where I fix the space V alpha. Okay, choose your favorite space for the approximation of function of a of a single variable. Well, so you see here for estimating the one principal subspace of the function U, what I do is I introduce an approximation space of functions of the first variable. I project the function U in this subspace, and I compute the one principal component of this. And I repeat this for all the leaves of the tree. Okay? Then when I am in a node, which is an interior node, not a leaf, I need an approximation space in which to estimate the principal components. What I will do is that I will consider the tensor product of the principal subspaces, or, sorry, a tensor product of the approximate principal subspaces that have been determined at the previous step. Here we had determined an approximation of principal subspaces associated with variable 2 and 3. When we look at principal subspace associated with a group of variable 2, 3, I look for these principal components in the tensor product of U2 and U3. Okay? Well, and at the end, when I arrive at the sums, when I have done the estimation of principal components at these two nodes that are the sums of the root, I just have finally to project the function U on the tensor product of these subspaces determined at these nodes to obtain an approximation. Okay? So we come later to the property of this algorithm, but I prefer now to say this is an ideal algorithm that you can use if you have an explicit representation of U and you want to compress your approximation at a given rank or a given precision. It is a variant of what was proposed by Lars and Wolfgang Hackbusch. So it's a small variant, but which makes feasible what is introduced now. Okay, a setting where we are not able to compute orthogonal projection of a function, but just evaluate samples of a function. Okay, so here I want to go in this sampling setting. So for having a feasible algorithm, there are two things to do. First, all orthogonal projections that you have seen previously, I will replace them by sample-based projections. So you can use here either interpolation or least square projections, whatever projection which is based on sampling the function. Okay. So I denote this new projection based on samples by this new letter I. This is a projection on the space W alpha. So this is no more an orthogonal projection, but an oblique projection. And here I just precise what is the form of this oblique projection operator. So this operator applied to a function, in fact, is a function that you can write as a sum of some coefficients times functions that are a basis function of your space V alpha on which you project. And this coefficient A alpha will depend on evaluation of your function on this particular point X alpha complementary that you consider, and on a set of points here that are samples of the group of variable X alpha, which could be interpolation points if you use interpolation, which could be also random samples if you use a standard least square projection. Okay, so for interpolation, and the result I will show you later, what I use is interpolation with a choice of the points here based on a magic points procedure. Okay, greedy algorithm for the selection of points that are adapted to the subspace on which we project the function. Second thing to do, so this is to estimate the principal subspaces. The principal subspaces, as I shown before, is solution of an optimization problem of our subspaces of an expectation of a distance square. Okay, So of course this cannot be solved exactly. Here we will rely on samples in order to estimate this optimization problem, and it becomes something like this: a minimization problem over all subspace of a certain dimension of an estimation of the expectation I have introduced previously. Okay, so an average of the distance square between partial evaluation of your function. Okay, so you sample a group of variable x alpha complementary. Okay, you evaluate the distance between this function of the remaining variables with respect to this projection. Okay, you take the square of the distance, you average this, and you obtain the functional to minimize. And this can be done. This can be done because U alpha is a projection of U which lives in this V alpha space, a finite dimensional space of low dimension. Okay, and here you just manipulate samples of your function. So in practice, what you have to do at this step, because U alpha is obtained by a sample-based projection, is to evaluate your multivariate function at a collection of points that are like this, associated with a particular sample of the group of variable x alpha and a particular sample of the other variables. Okay? So the algorithm only requires evaluation of the function at this point, but these points are selected adaptively. At each node of the tree, you will select the new points at which to evaluate the function. So here is the first theorem about the property of this algorithm. When you work with a prescribed rank. So here, this theorem is under an assumption, which is not so trivial to verify in practice. There are some partial results about the condition on the number of samples you have to use in order to have this, but let me assume that we have this property, that the subspace U alpha that you have determined at the node alpha, when you do when you estimate your principal components, you suppose that this space is almost optimal. Okay, it's quasi-optimal. I mean, this minimization of over all V with the alpha rank bounded by R alpha, okay, that minimize the distance to the U alpha. The solution of this is associated with the truncated singular value decomposition. What is behind this is the principal subspace. What I assume is that the U alpha is not too far to the optimal space. Okay, up to a certain constant C, which is here. So of course, because you are in a statistical setting, you will not have this property almost surely, but just with a certain probability. Okay. Then if you have this assumption, then you can show that the algorithm provides an approximation U star with an error to the square, which is bounded by these two terms. Here you recognize a term which is due to the discretization error, the choice of the spaces V nu you have done at each of the leaf. Okay, if you have used wavelet spaces or polynomial spaces for approximating univariate functions, you pay something here. Okay, there is a discretization error here. Here what you see, this term is the best approximation you can expect from your tensor format. Okay, this is a minimal error in the set, in the tensor format I have introduced before. And of course, these two terms are amplified by some constants. Here you have the constant C, which is here. Here you have the cardinal of T, which is the number of nodes that you have in your tree. Because the result that you see here, in fact, is obtained by a first step where you bound the error by a sum of terms, a sum of errors that are associated to each estimation of the principal subspaces at each of the nodes. So you cumulate the error in this way of proving this error bound. So this is why you see the cardinal of T here. And you have also two constants, lambda and lambda tilde, which are associated with use of sample-based projections. Okay. If you use interpolations, they are related to some kind of Lebesgue constant of your interpolation operators. And okay, let's say it in a more general terms. These are associated with norms of the oblique projection operators, or the distance between these oblique projection operators and the orthogonal projection. Okay, if you really use in this algorithm the orthogonal projections, the lambda and the lambda tilde are equal to 1. Okay, Well, so just a comment here about complexity. When you use interpolation, that means that the number of samples, if you use interpolation, and if you use for the estimation of the principal subspace just the minimal amount of information, which is how many partial samples of a function do you need to estimate a subspace of dimension R alpha? You need at least R alpha functions. Okay, so number of samples you can choose as a minimal amount of information equal to the rank you have specified. If you do this and if you are in the context of interpolation, the algorithm will only evaluate the function at a number of points which is exactly equal to the storage complexity. Okay, at the end you obtain an approximation which is not equal to the functions where you have evaluated the function. So it's not interpolation, but the number of points you have evaluated is exactly equal to the storage complexity. Okay. Well, so here is just, I will not go into the details. So what I said about the constant lambda and lambda tilde, I said they are associated with they are kind of Lebesgue constant associated with your oblique projection operator. What is known is that when you do interpolation in high dimension, the Lebesgue constants behave dramatically. But if you look at precisely the expression of these constants, you can find the paper. I will give the reference later. In fact, they are not precisely the usual Lebesgue constants. They are, in fact, the norms. They are norms of operators restricted to specific subspaces associated to the function you are trying to approximate. These subspaces on which you restrict the operator are the so-called minimal subspaces. This is a concept that had been introduced by Hackbush. You can see these subspaces as the smallest subspaces that are required to represent your function you try to approximate. And in fact, the nice behavior of the algorithm you will show is due to the fact that for most of the function I considered here, the minimal subspaces are quite nice, so that the interpolation operators or oblique projection operators I use are very nice property on these subspaces. So there will be cases where the spaces here are awful and the algorithm will behave in a bad way, in the sense that the lambda could be very high, but in practical situation, very often these lambda and lambda tilde are moderate. And what you can show is that when in the case of tensor recovery, which means that if you have introduced approximation spaces on the leaves that are able to represent your tensor, which means you have no discretization error. If you are in this case, plus if you consider that the samples of the function you do here to estimate the PCA produce linearly independent functions, then you can, in this situation, you can show that the space that you have will be exactly equal to the minimal subspace of U, and you can prove that all the constants you have seen in this upper bound here, in this error bound, are equal to 1. Okay, and this I will try to illustrate on the first example here, which is the approximation of the so-called Henon-Hilles potential. So if a function of d variables, you can see here that it's a polynomial approximation in these d variables up to degree 4. Okay, so if I use approximation spaces that are polynomial spaces at least of degree 4, I make no discretization error. Plus, what you can show also is that if you use this particular tree, the ranks associated with the red nodes here, in fact, are equal to 3. You can show it relatively easily. So here, for this function, I know the rank. It's equal to 3, 3, 3 associated with this format, which is a tensor train format. And I know that it's a polynomial of degree 4. So I run the algorithm with polynomial approximation of degree 4 and a rank 3, 3, 3. And I observe here the results, where in this first table that you see here, when I estimate the PCA, so principal subspaces I want to estimate are of dimension 3, so I will just use 3 samples. I just use the minimal number of information I need. This gamma is here in this table. This oversampling with respect to what you need, the minimal information you need. And so in this situation, because I use interpolation, the number of samples I use is equal to the storage complexity. And here you see the error multiplied by 10 to the power 14. So what you see for different dimensions here is that the error behaves like 10 to the minus 14, 10 to the minus 13. Okay, so almost recovery at machine precision. Okay, whatever the dimension, you see. So here, if you increase the number of samples for the estimation of the principal subspaces, you can see that you can improve these results and obtain something of the order 10 to the minus 14. I should mention that why you see intervals here is that because the algorithm is random, so I run the algorithm many times, and what you see here is the confidence interval for the error. Okay. Well, so this was for the tensor recovery setting. Now maybe something more interesting is that if you want to prescribe a precision, you want an approximation at a given precision, you don't know the range which is needed for reaching this epsilon. So you want to prescribe the epsilon. What the result which is here is that if you perform the PCA at the node alpha on your approximation of the function u, which is u alpha, such that the space you estimate gives you a relative precision of epsilon divided by the square root of the number of nodes of your tree. Okay. Then, and also if your approximation error, your discretization error is below a certain accuracy, epsilon tilde, then what you obtain is something with an error which is bounded by two terms. The term associated with the truncation you do when you perform your PCA, and this term which is due to discretization error, with exactly the same constant as before. Okay, so if you want a precision epsilon, you will pay a constant related to this interpolation or oblique projection operators you have used. Okay, so how to do it in practice here? In practice, you can rely on cross-validation methods, for example, to control this precision at this step. That means you will select the rank, the dimension of the principal subspace to select with respect to some error criteria. Okay. Well, so an example here, the borehole function, which it is a function of 8 random variables that model the flow through a borehole. So here you see the probability law of the 8 variables. Here I use a format associated with a linearly structured tree. So the rank is imposed for all the nodes that you see here. So it gives you a format which is like this, not so important. Here I use polynomial approximation on the leaves with a certain degree. And here you see the results where we run the algorithm with a prescribed precision. So here I say I want a precision 10 to the minus 4. You run the algorithm, and the algorithm will select automatically the ranks when it will perform the different PCA on the nodes. And what is provided, what gives the algorithm is an error which is with high probability in this interval 10 to the minus 5. So here you see that you are below the prescribed precision. So sometimes 10 to the minus 3, the algorithm gives you something which is a slightly higher error, but whatever the precision you ask here, you see that the algorithm provides something of the order of the precision you have prescribed. This is a final storage complexity of the approximation. So for 10 to the minus 4, the number of parameters in your format is about 100, and the number of samples is about 3 times the number of parameters in your final approximation. So you see that the number of evaluations with respect to epsilon scales in a very nice way. Okay, to reach 10 to the minus 10 error at about 2,000 samples. And you see here, for indication, the average rank, which is produced by this random algorithm. This is selected automatically. So if you had to have an intuition about the rank of a function like this, when you have a black box computer code, okay, this would be clearly a combinatorial problem, I would say. Okay, to select, to say that, okay, the rank associated with the fourth variable is 8, the rank associated with this one is 2, etc. So clearly this is a very difficult problem to say a priori what is the rank which is required. So this algorithm with a prescribed precision select the rank adaptively. Okay? So here is just some slides about an illustration of the influence of the tree, because the algorithm runs whatever the tree you choose. So the choice of a tree is a very critical issue, very critical questions. There are some problems where you can show that a function can have a very low rank in a particular tree, but in another tree you will have a number of parameters that scale exponentially with the dimension d. Okay, so in this situation, for this borehole function, the things are going well, because whatever the tree you choose, whatever the permutation of the dimension you do, the error you obtain here when you specify 10 to the minus 8 is around what you have specified, with a number of samples which is always of the same order, okay, 1000, 2000, 3000. But this is not the case for other functions. So here I just mentioned some work in progress. So what you have seen that this algorithm is not guaranteed. If I have the precision epsilon, it gives me something of the order of epsilon, but not epsilon, because there are these amplification factors, the lambda, which can be evaluated in practice. This has not been done here, but currently we are trying to provide implementation where these lambda are estimated on the fly, so that you can rectify the error on the fly in order at the end to obtain this epsilon. Of course, something more important is to have a priori estimation of the complexity of the algorithm for classes of functions. The results I have shown are true for any function, okay? But there is no indication about, for a particular function, what is the number of samples I will require to reach this precision epsilon, okay? For this you have to do assumption on the classes of functions. So this is a complicated question, but a crucial question here, because if you have 10 to the minus 5, this algorithm that I showed you is able to do it, but you don't know how many samples it will use, okay? So maybe you will let it run for millions of years, you don't know. So to have some information about a priori complexity, we have to do some assumption. And also the tree selection, which is not crucial in the borehole function, but which is crucial in other situations, like the n-nihilist potential, for example. Here I used the tree which was adapted to the physics, in fact, underlying physics. But sometimes we have no idea about the tree to choose, and this becomes a combinatorial problem for which we need some heuristics. Thank you for your attention.
Okay, questions, comments?
Very, very interesting. Just a comment. Your lambdas were the mu factors in Peter's talk. In other words, depending on what kind of samples you use, you can take that space spent by the samples and compare it with your current space on which you interpolate.
On which you project it.
Or it's just that angle.
Yeah. Yes.
So that is another singular value decomposition of a cross gradient that would give you these factors.
Yes, this is precisely this. In fact, when I say we are able to estimate them,
Right.
this is an eigenvalue problem that you have to solve. Yeah.
But you could do that.
Yes, we could do. We did not do this here. But
Any idea of what benchmark classes should be for this algorithm to perform well?
to perform well?
Yeah. I mean, when you ask for a priori,
Yeah.
what would be the generic classes which you target with this? So,
In fact, what we
in a way,
for interpolation,
say the solutions from these parametric diffusion problems, they would, for fixed number of parameters, they would be excellent.
yeah, this works well as
Then you get even an exponential convergence.
yeah, yes,
Correct.
yes. For this problem, I would say this algorithm, when this error behaves well, which is the case of this parameter-dependent PDE, so usually this algorithm reaches the same thing that you could expect with a Galerkin approach or something like this. So you pay with the constant here, but in these problems, things are so smooth that this lambda and lambda tilde seems to be really, really small. okay, which is the case of the borehole. You see, there is the effect of the lambda is completely negligible. Okay, there seems to be around 1. So, but I have no idea about. It's the same question because when I do interpolation, I rely on magic points, for example, and this is the same question as having some a priori estimate of this growth of the lambda for these interpolation points or interpolation operators. For the moment, I have no idea.
Maybe one more question. What one way to mitigate, say, that effect of the Bay constants which you have in interpolation, if you to keep the polynomial degree lower than the space and do a least square lower than the number of the measurements you have, and do a least squares.
With the number of measurements less than the dimension?
So the number of measurements should be larger than the dimension from which you approximate. And you can't interpolate, but you can do a least squares.
Yeah.
And that keeps that usually that factor lambda.
Yeah, what we are working on that actually is to do least square, but kind of optimal least square, because least squares, the number of samples can also not grow linearly with the dimension of the space.
Typically, the number of samples is twice as large as the dimension of the space on which you do least squares.
Yeah, this is not, depends on the, you have to say some assumption on this, but what we are working on is trying to introduce optimal least squares so that indeed with a number of samples in n log n, you are quasi-optimal. So we try to kill the lambda actually at the moment. Yeah.
One more question?
This is a slightly philosophical or maybe sociological question. I mean, statisticians, at least, are not very familiar with bounds where the probability comes from the randomization. I mean, we are and we are not. I mean, so this reminds me, although of the early days of machine learning, and where you would measure where the bounds, the constants in your concentration inequality would have something like Chernovenki's dimension and
Yes.
things like that. So when you say you're going to investigate the
Yeah.
complexity a bit more, are
Yeah.
you going to use not just the Bayes constant but other things as well?
Yeah, in fact, indeed, the partial results we have here are based on concentration inequality, about the number of samples we need to achieve this. These are current works. There are no, but we have partial results about results in probability like this. But for the moment, we have quite pessimistic results in the sense that the number of samples you need will grow polynomially with the dimension of the space you want to estimate, which is completely unrealistic and far from the observation of the example I showed you. Okay. In practice, we observe in the application I have shown here that the number of samples you need to estimate, let's say 10 principal components, is of the order of 10. But the theory we have at the moment tells us that we need 1 million samples, okay, which is not really useful. Yeah.
It may have to do with the fact that nobody has a good estimation for the BC dimension for low-rank functions. Because I think the BC dimension is much lower than what you get by trivial estimates based on linear spaces.
It's lower, you say, because I don't have in mind the result. Reynolds Schneider recently had this estimation of the VC dimension.
He had?
But it is of the order of the storage complexity, I guess.
I mean, I once checked the papers on what's the VC dimension of the level sets of polynomials, and it's related to the degrees of the polynomial.
Yes.
VC dimension, right? That's
Yes.
what they say.
No, but yeah, the estimation of
epigraph for linear spaces. But these tensors
are based on linear
they are
subspaces.
based on linear subspaces, so it should be. But it's not so clear how the dimension of the linear subspaces goes exactly into the VC dimension of that nonlinear set of approximation.
It's more the estimations that are available. I don't know if this is published or not. That's why I give you an information I'm not sure about that. It's more about the covering numbers, of this type of tensor format that have been obtained. So maybe it's more covering numbers, but
I suggest that the conversation and questions continues over lunch. Let's thank Anthony again.
thank you.